Hello, this is Jason Kendall, and I'd like to welcome you to my Introductory Astronomy lectures. You're about to begin a wonderful journey with your start in the hobby of amateur astronomy. There are fewer more enjoyable activities than just going outside to see the night sky. You'll see the stars rise and set as they move slowly across the sky. Perhaps you'll see a shooting star, perhaps you'll enjoy the moon in one of its many phases. Perhaps you'll be so fortunate as to see a comet. To enjoy this hobby, you don't need a telescope, you don't need a camera, you just need time and a dark sight. Go to the darkest place you can find where you can see a lot of stars and just begin looking. That's the basics of observational astronomy. Get away from all the bright city lights as far as you can so you can see pictures like this. These are the stars from Boulder, Colorado. I took this 60-second exposure using a DSLR camera on August 16, 2017 at about 11 p.m. from the mountains above Boulder, Colorado. Boulder is the sky glow off to the left. The little dots across the horizon are a couple of planes flying near Boulder International Airport. We can also see, in addition to the tree in the foreground, some people's houses in the background. More prominently, we see the Milky Way centered up, rising from the horizon. That's not smoke, that is the Milky Way. Very often when people first see the Milky Way, they think it's smoke, especially people who've lived in cities their entire lives. They just can't believe it when they see the Milky Way in the sky in a very dark location. But if you also go outside on such a dark night, and you can find a place that's hopefully nearby, you'll see it too. You'll also notice that you get lost trying to count the stars. This image alludes that if you scanned around the sky in a truly dark place, you would probably find that you'd see 2,000 to 4,000 stars. Most places are blighted by urban light pollution these days, but you can still find several places if you go hunting for them, and I suggest you try. Navigating around this image, just behind the trees, is the teapot shape of Sagittarius, and off to the right, the bright star above, straight up from the hill. It looks kind of reddish in between the stars that are bluish on either side. That's Antares, the heart of Scorpius. The pincers of the scorpion are almost to the edge of the screen, off to the bottom right. If you look at the two lights that are close together on the horizon, those two almost bright yellow lights, and then if you look straight up from them, you see what looks like one of the brightest things in this picture. That's not a plane. That's the planet Saturn in the constellation of Ophiuchus, which lies just between Sagittarius and Scorpius. When we look out into the night sky, we can certainly see quite a few things. Now, how would I exactly point out to you which thing Saturn is in the sky? How could I be certain that you're seeing it, or Antares? To help us communicate, we have two things to use: how high it is off the horizon and where it is along the horizon. This forms the basis of what we call the horizontal or altitude-azimuth coordinate system. Now, if I mark Saturn with this green bar to show its altitude of the horizon, we have the first of our needed measurements. We can ask, why does the bottom tick mark, which should be the horizon, go below those hills? One might think that the horizon should be at the top of the hills, but it's not. Perhaps a better way to think about it is the horizon can be defined to be 90 degrees down from straight overhead. That overhead point is called the zenith. So if you measure down from the zenith to the hilltops, that'll be less than 90 degrees. I've also marked south. That means due north is directly behind the viewer in this picture. We could measure angles from the south that are marked along the horizon, but we choose north instead, due to the ease of finding the North Star. Therefore, we can say, what is the angular measurement along the horizon from due north to the bottom tick mark of the line below Saturn? Well, we need to choose a direction. The direction we'll choose is north to east to south to west, then back to north, or clockwise as seen from above. In this image, we'd measure from the tick to the left until we got to due north. Given the date, time, and location on Earth, this works out to be roughly 210 degrees. We call this angle azimuth. We could also measure that Saturn is 69 degrees down from the zenith, which means it has an altitude of 21 degrees off the horizon. It's important to note that the altitude and azimuth angles of almost everything in the sky are always changing and are always different for different observers on the Earth. And lastly, they're never the same from one night to the next. However, there are two notable exceptions, and I'll let you ponder that. Another name for altitude and azimuth is the horizontal coordinate system. Now let's define the horizontal coordinate system properly. We can imagine the sky as being a dome overhead, with the horizon all around us. We then find north using a compass, or much better using the North Star. Now we're ready. We need to have a good way of measuring angles too, but let's leave that aside for the moment. To find the coordinates of some star in the horizontal system, we measure the angle from north towards the east, i.e. clockwise looking down from above, until we get to the point on the horizon directly below that star. That'll be our azimuth angle. Next, we measure the star's altitude up from the horizon, or if you wish, 90 degrees minus the angle between the star and the zenith. In the diagram, the azimuth is less than 90 degrees, because it looks like we didn't even get to due east. Let's call it 60 degrees, just to assign some reasonable number to guess with it. Likewise, the altitude looks to be maybe 50 or 60 degrees. You might ask why we even have or even need this coordinate system. Perhaps you found a comet and wish to tell some friends nearby on the phone where to look in the sky. So long as they were not too far away from you, this should work pretty well. If they're hundreds of kilometers away, then it won't work, and we'll need a better way of telling distant friends who will try to look for it tomorrow night. A good way to think of altaz, as horizontal coordinates are known in shorthand, is to call them local observatory coordinates. They're important to you at your observing site because when things are low in the sky, i.e. a small altitude, there's lots of atmosphere between you and space, so things are dimmer close to the horizon. You might find that you want to observe things that are at least 30 degrees above the horizon. Why? Maybe the observatory has a big tree that was planted by the founder decades ago, and the board of the observatory's location has decreed that the tree cannot be cut down for your use with stargazing. Therefore, you have to plant around the tree. While this may sound silly, there are examples throughout amateur astronomy where you need to wait until the object gets much higher in the sky before you can observe. It's mostly the case that the atmosphere dims, blurs, and reddens low-altitude objects. In general, we like observing things as high in the sky as we can. This goes by way of saying that when planning observing runs as an astronomical observatory, you always want to optimize your viewing for your location. Again, the altaz of a star, comet, or planet in the sky constantly changes and isn't the same for different observers at different locations on the Earth. Let's now put the idea of the horizontal coordinate system into practice. Running in the background is Stellarium, which is a free sky simulation software. We're going to look at the azimuth and altitude of various stars. These are the stars at a given place, the place of the observer, somewhere on Earth. What we see across the bottom of the screen is the horizon. The horizon is demarked by various little red letters. The capital letter E denotes east, SE denotes southeast, and northeast is denoted by NE. From the date time clock in the upper right, we see that it's somewhere in December 2034. We also see that the time is speeded up and the stars are moving fast. The numbers in the clock that are scrolling by quickly are hours, minutes, and seconds. It's set to run at approximately 10 minutes per second. I've also turned off the atmosphere so we don't get the glare of the sun. I'm doing this, of course, because I want to focus on the positions of the stars in the sky and how they change with time. The current location is New York City. We'll change that location around shortly. You can see the location in the lower left. Now let's focus on a couple of stars in the sky. The current time is about 7 p.m., and I'm going to pause the time and take a look. As you can see, there are labeled stars rising in the east. Let's use Beta Taurus. Now, I'm going to turn on our angle measurement to see how high off the horizon Beta Taurus is. I'm going to place one end of it on the star and bring the other end of it all the way down, straight down to the horizon. We don't want to go side to side, just straight down. It says it's about 48 degrees in altitude, and that's a good first rough estimate. Now let's turn that off and click on the star itself. We see that Beta Taurus, which has a proper name of Elnath, has a current altitude of about 47 degrees and 56 minutes, almost 48 degrees. That's very close to the rough estimate that I used with the angular measurement bar. In the upper left, Stellarium is telling us that Elnath is 48 degrees off the horizon. And its azimuth angle is 90 degrees, and that's because it's almost due east. Let's stick with Elnath for just a minute. Now, what I'm going to do is I'm going to bring up the location window on Earth, and you can see on that map a red arrow pointing roughly at New York City. Let's now change the location by changing only the longitude and go straight west. We go over the Midwest and end up in the mountain states, and let's pause here. We're now maybe over Colorado or Utah. That seems to be good. Let's put Salt Lake City into the search and see that location. Hey, I was pretty close. So we have a marker on Salt Lake City, Utah. Oh, and by the way, the Greek letter and the abbreviation is the Bayer designation for a star, typically for the bright ones. Elnath is its common name, but its Bayer designation is Beta Taurus. Here, in Utah, it has an azimuth angle of 69 degrees, so that's north of east. It also has an altitude of 20 degrees. So this is why you can't tell someone over the phone who is at a distant location on Earth to go outside and look for a star at the altitude and azimuth that you measure locally. To further demonstrate, let's just go way far north. We're just going to increase the latitude. Let's end up in northern Canada, the Great White North, and warm up with some Tim Hortons. We'll see that the star's location didn't change much. It did change the azimuth angle a bit, and it changed the altitude a bit. But now, if we scoot back over north of New York City and see it from that location, see how the star's positions change as we careen around North America? Now, if we observe it from western Greenland, the azimuth angle is 140 degrees and the altitude is 47 degrees. If then we jump to somewhere in Brazil, that's way over there. It's 38 degrees above the horizon, and its azimuth angle is 34 degrees. It's in somewhere in the northeastern part of the Brazil sky. So okay, let's go over to Western Europe. Where the heck is it? It's somewhere else now. We'd have to probably swing farther around to find it in the sky. As you can see, for different locations on the Earth, for the exact same time, the position of the star in the sky changes. Let's go back to our original location, New York City, still looking at Beta Taurus. On this date, December 6th, 2034, at 2100 hours, that's roughly where it would be in the sky. Let's get rid of this location window and we're going to speed up time again. Now let's look to the south. We see the constellation Orion with some familiar stars. They're floating east to west. If we look to the west, we see things setting, which means their altitudes are decreasing. Stars ascend in the east and descend in the west and go laterally across east to west along the south. Now we finally look north. I want you to note there's one little star about which everything seems to be rotating. All the stars seem to go around Alpha UMI. That's Polaris, the pole star. It has an azimuth angle of roughly 0 degrees and an altitude of 40 degrees. The altitude of the North Star, or Polaris, is a great measure of your latitude. Your latitude on the surface of the Earth is determined historically and very reliably by the location of the North Celestial Pole off the horizon. For New York City observers, that star is approximately 40 degrees off the horizon. Now, if we move further and further north, we see that Polaris goes way up in the sky. If we go up to, say, 70 degrees north latitude, we're far north, but not yet at the North Pole. If we want to see what that looks like, let's zoom out just a little bit more, and now let's keep going north until we get to 90 degrees north latitude. When Polaris is at the zenith, you are at the North Pole. The zenith is where all the lines of azimuth converge, and about which all circles of altitude are centered. The zenith is simply the point that's straight overhead. Polaris is important because it is located in the sky next to the North Celestial Pole, which is the place in the sky that all stars revolve around. Suppose we go further south, down to, say, 10 degrees north latitude. If you're at 10 degrees north latitude, you're somewhere right above South America. And if we go to, say, Quito, Ecuador, which is on the equator, here the north celestial pole is exactly on the horizon at 0 degrees altitude. If we then go south of that, Polaris is now below the horizon. So now what do? You can't measure your latitude that way. Now let's swing all the way around and look due south. Now we find there's a different location in the sky that stars seem to be rotating around. That's called the South Celestial Pole, and here the altitude of the South Celestial Pole is your latitude in the southern hemisphere. We see that there are no bright stars that are associated with the South Celestial Pole, however. That's sad, because it makes it difficult to find out how to find our latitude. However, there are some tricks. You can use the Southern Cross, which is an asterism that points roughly at the South Celestial Pole. More on that another time. Let's go back to New York City, but we're still looking south. So there's Orion once again coming across. Let's just stop time once more and say, what is the altitude of, say, Rigel right here off the horizon? I'm going to get that angle measurement again to solidify the idea. The altitude of Beta Orionis, or Rigel, is approximately 39 degrees off the horizon. It has an azimuth degree of 160 degrees and an altitude as roughly measured of 39. As you've picked up by now, the horizontal coordinate system is only suitable for local observers. It isn't a coordinate system that we can use to communicate locations on the sky between people that are separated by any great distance on Earth. Next time, we'll look at the first attempts to help people communicate locations in the sky, and they did that with constellations.